Okay, let's try some problems from section 6.2, starting with some problems from the textbook, and then we'll look at some hard problems from the homework. Okay, so starting off basic, number 1 from the textbook. Okay, so we're given these four curves, y equals x plus 1, y equals 0, x equals 0, x equals 2. So we first find the region enclosed by these curves, then we rotate it around the x-axis, and we want to find the volume of that region. Okay, so if we go through our steps, I laid out some steps in the lecture. I kind of forget the exact order I laid out, but we always want to start with drawing our region. Okay, so y equals x plus 1, that's just this line. Okay, slope 1, y-intercept 1, okay. Y equals 0, well that's, let's see, that's the x-axis. Okay, x equals 0, well that's the x-axis. And then x equals 2, that would be the line through the point 2. Okay. So what's the region enclosed? Well, there's only one answer. It's this region here. So I'm looking for, well, I'm starting with this region, then I'm rotating around the x-axis. Okay. So let's see. Once I do that, okay, let's say this is my x, this is my y, and this is my z. I rotate it. Actually, I'm not even going to draw it like this. I'll just stick with this. And then when I rotate my region around my x-axis, let's see. Okay. I get some sort of 3D object that looks like this. So kind of like a megaphone or something like that. Okay. Now consider the cross sections. So we've rotated around a horizontal line. So everything I want to do, I want to do everything in terms of x coordinates, right? I want to do ax dx. I want to integrate in terms of x. All right, so that means I need to take cross sections going along the x-axis. Okay. All right. So what are these cross sections look like? Well, if I take a cross section, look at and lay it flat on the page, I can tell it's going to be a solid disk. Okay. So I need to use the formula pi r squared. Okay. So what's the radius of my object at each point, my cross sections? Okay. Redrawing our object real quick. Looks something like this. Okay, so let's say I take a cross section here. The radius is going to be the distance from here to my curve, right? Well, that's just the y coordinate of that point on my curve. And since I need to write everything in terms of x for my integral, instead of writing y, okay, I know, let's see, I know y is going to be equal to x plus 1, right? So that y coordinate is given to me by this. Okay? So my radius is going to be x plus 1. All right. So now I know my integral is going to look something like this. Now I need my bounds of integration. well, my object's starting at 0, then I'm integrating until the end of my object. Okay, what's that point? X equals 2. Okay, that's coming from this vertical line here where our region ends. Okay, so I need to integrate from 0 to 2, pi x plus 1 squared. I can pull the pi outside. I can just multiply everything out. I don't need to do a u substitution. I could do a u substitution, but it might be easier just to multiply everything out. Then integrate that stuff. From 2 to 0. Okay. All right, and then let's see, simplifying this fraction. Let's see, 6 is 18 over 3, so I got something like this. For the rest of the problems, I'll try and follow the steps a bit more closely and not explain as much. Okay, let's try problem 7 from the textbook. So I got y equals x cubed, y equals x greater than or equal to 0, and I want to rotate around x-axis again. Okay, so let's follow our steps. These steps are just a guideline. These are what I do if I'm trying to be methodical about everything. Okay, so you don't have to follow these. I think they're a good guideline. Okay, so y equal, I'm going to draw the region first. Let's see, y equals x is that line. Y equals x cubed. Maybe it looks something like that. I can draw this better. Let's see. Let's draw y equals x cubed first. Okay, and y equals x probably looks, that's probably going to look something like that. Okay, and then since we need x greater than or equal to 0, I'm just dealing with this region in here. Okay, so I can forget everything else. I can ignore that side and just confine myself to this region. We might have done this one in the lecture already, but we can do this real quick. Okay. All right, step 2, do my rotation. Okay, so when I rotate that, what do I get? Okay, it's kind of like a megaphone again, but now we got this empty, we got some empty space. We got a lot of empty space. So my cross sections are going to be washers, right? Okay. So maybe just by looking at the object, I can do step 3. I can determine that these cross sections are going to be washers. Next step, I need to find my outer radius, inner radius, right? So remember that when we're measuring outer radius, inner radius, we measure from the line we're rotating around, which in this case is the x-axis, and then we measure it to our curve. Okay, so outer radius is that blue line, and then let's say, excuse me, inner radius is that blue line, and then outer radius would be that yellow line. Okay, so what are these distances? Let's see, that blue line is the distance from the x-axis. If we go to this 2D object, it's the distance from the x-axis to this curve, right? Okay, the y-coordinate, so we need that y-coordinate at that point. And since we want to integrate in terms of x, instead of writing y, I'm going to write this, x cubed. Okay. All right, so inner radius is x cubed. What's outer radius? Well, that's the distance from the x-axis to this curve, okay, which is just the line y equals x. Okay, so my outer radius is going to be x. Okay, so now I can write my area function, right? Area of the cross sections in terms of x would be pi rho squared, so pi x cubed squared. Oh, no, excuse me, pi x squared, rho is x, minus pi ri squared, so minus pi x cubed squared. What are my bounds of integration? Okay, where am I integrating from? I'm integrating along the x-axis, okay? So let's see, where does my object start? There. Where does it end? There. Okay, where are these points? They're going to be where my curves intersect, right? So maybe it's obvious they intersect at 0 and 1, but the way to formally do it is set x cubed equal to x, move everything to one side. Let's move it to the left side. And then solve. Okay, so this has solutions x equals 0, x equals positive 1, x equals negative 1. Since in the beginning we had this condition, x greater than or equal to 0, let's go ahead and eliminate that one. So we have these 2 points where our curves intersect. So my bounds of integration are going to be 0 to 1. Okay, now I have all the information I need to set up my integral and integrate. 0 to 1 pi x squared minus pi x cubed squared. Okay, we can go ahead and simplify this integral, pull out the pi. X cubed squared is x to the 6th. Okay, so my integral is this, integrating. Let's see, common denominator 21, so let's see, 7 over 21 minus 3 over 21, right? So 4 over 21 times pi should be our final answer. Okay, let's try a couple from the homework. Let's do number 9 on the homework. So I got y equals 27x cubed, y equals 0, x equals 1, rotated around x equals 2. Okay, so let's draw our region, our 2D region. Okay, 27x cubed. Okay, this is just a really rough approximation. It's basically going to be the same as x cubed, but maybe stretched certain ways. Let's see, stretched vertically, I guess. And then let's see, y equals 0. Will that just be the x-axis there? And then line x equals 1. Okay. Okay, it's going to look like this. Now, this is not to scale. This point of intersection is going to be kind of far up. But this is enough to get an idea of what's going on, what my region, my 2D region is going to be. It should be this thing. Okay. All right, and then let's see, I want to rotate around this line. X equals 2. All right, so that's my step 1. Step 2, let's go ahead and draw our 3D object. Okay, so I'm starting with this, and then I'm rotating around that line, y equals 2. So I should end up with kind of mirror image like that. And then my object should look like kind of a volcano type thing. Kind of like this. With an empty cylinder in the middle. All right. So let's see, I've rotated around a vertical line, so I want to do everything in terms of y, right? I want to integrate in terms of y, and I'm taking my cross sections going this way. So when I take those cross sections going up vertically, my cross sections are going to be washers, right? Because there's some empty space in the middle. Okay, so 3, I figured out that my cross section should be washers. Okay, now I need my outer radius, inner radius. Okay, what's the outer radius? Outer radius, okay, would be, let's just kind of clear things up a bit. Okay. I'm rotating around that dotted line. My outer radius in yellow would be the distance from here. Oh, let's measure it going this way. Okay. The distance from this point to this point. Okay. Well, this point here is on that curve y equals 27x cubed, right? Okay. So let's see. Let's do this green distance here. This green distance would be 2 because this is the line x equals 2. So that green distance is 2. And then if I subtract away this green distance, I should be left with my yellow line, right? Okay, so what is this little green guy? Well, that would be the x coordinate of my point here. Okay. Okay, so what is that x coordinate? If I have y equals 27x cubed, then let's see, I want to solve for x. Okay, so I'd have cube root of y over 27 equals x. Okay. So my outer radius should be, okay, this, excuse me, it should be 2 minus that. What's my inner radius? Inner radius is much easier. It's just distance from here to here, okay? That's always 1, right? No matter where I am on my object, that's always just the distance from x equals 2 to x equals 1. So that inner radius is always 1. All right. It might help to simplify this a little bit. Okay, so this is 2 minus, well, let's see, cube root of y over, what's a cube root of 27? That's just 3. Okay, so we could write this as this. All right, 5. Let's go ahead and write our area function. Okay. 6, what are my bounds of integration? Where do I want to integrate from? Well, I'm integrating in terms of y, right? So let's go over to this 2D object. I should be integrating from here to here, okay? What are these points? Well, let's see. This point is at 0, obviously, y equals 0, okay? And what's this upper point here? Well, it's where the curve y equals 27x cubed meets the line x equals 1. So basically, I just take x equals 1 and plug it into this thing, and I get y equals 27. Okay. And then this is enough to form my integral. So I have this integral, and let's go ahead and square this. And let's go ahead and pull out the pi. Sometimes I need to write this stuff out to see how it squares. So don't be afraid to do that. Okay, so I've pulled out a pi from here, so that becomes a 1. Okay. And then I'm squaring. This is my squared term. Okay. So I get this thing, and then integrating. Okay. I got a 4/3 here, and I'm dividing by 4/3 here, so those cancel, thankfully. I'm just left with y to the 4/3 plus, let's see, okay. Now plugging in my bounds, say 3 times 27, that should be 81, minus 3 to the power 4, that should be 81 as well. Let's see, if I take cube root of 27, that's 3 to the power 4, that'd be 27 times 3, that'd be 81, yeah. And then what's 3 to the 5th? That'd be 243. Okay, so these cancel. I should be left with 243 over 15. which should be 81/5. Yep, and that checks out. So this one, it's pretty ugly. Hopefully this helps. Like I said, I don't control the problems on the homework. Hopefully this will give you some clues on how to solve your version. Another one that seems to confuse people a lot on these homeworks, I've taught this course a few times now, and people get confused on number 10 as well. So let me pause this and draw this thing. Okay, so we're given a drawing that looks kind of like this. I've tried to replicate it as best as I can. And we're told to find the volume of the object that we get when we take the region R3 and rotate it around the line AB. Okay, so say R3 rotated around AB. All right, so it's the same type of problem we've been doing before, except maybe it looks a bit more abstract now. So we're going to take this yellow region and rotate it around this line, this vertical line here. Okay, so let's try and do the same exact steps. Okay, one. Okay, I've already got my 2D region. It's this yellow thing. 2, let's try and figure out what this would look like in 3D. Okay, so I got this, I'm rotating around this vertical line. Okay, so I'm starting with this, I'm rotating around this vertical line. Let's leave this as a dotted line. Okay. When I rotate this region around my vertical line, I get something like this, and then, okay. So it'd be kind of this upside down bolding. And then there'd be some empty space in here because the walls of this bowl look like this. Okay. Okay. So I've rotated around a vertical line, so I want to do everything in terms of Y. If I'm taking cross sections like that, I lay them flat out on the page. Okay, I see there's empty space in the middle. It's going to be a washer. For outer radius, inner radius. Okay, let's go back up to this 2D thing. All right, if I'm rotating around this line, okay, let's talk about outer radius first. Okay, measuring from this line to my original 2D curve. Okay, outer radius will be this distance, right? Okay, well, what is that distance? If I had this white line, okay, that distance would be, the distance of this white line is just, okay, from this x-coordinate to this x-coordinate. Well, what is that x-coordinate? It's 1. Okay. All right, so I can tell this is the line x equals 1, this dotted line here. Okay. All right, so this full white line here would be 1. And then if I subtract away this, which is the x-coordinate of this point, I would have just my outer radius. And I would have, okay, the remaining white line. All right. So what is this distance, this x-coordinate? Well, the x-coordinate is given by this. Oops. Okay. Remember, my curve here is, what was it? 2 4th root of x. Okay. And I want to find out what the x-coordinate of that is. Okay, so I need to solve for x. Okay. So my x-coordinate is given by this. So my outer radius should be 1 minus that thing. What's my inner radius? The inner radius is this distance, okay, which again I can think of as, okay, this line minus this piece, and that piece is the x-coordinate of that curve. Okay, what now I need to figure out what the equation of this line is. Okay, it goes from the origin to the point 1, 2. So this curve should be y equals what, 2x? Okay. All right. So my inner radius, okay, if y equals 2x, then y over 2 equals x. All right. So my inner radius should be 1 minus y over 2. All right. Now I can write my area function. What are my bounds of integration? Where do I want to integrate? Let's go back up to our 2D thing. Let's clean this up a bit. Where do I want to integrate from? My object, let's see, is going to exist from here. Okay, so let's say from here to here. Okay, what is that distance? That is going to be from y equals 0 to y equals 2. All right, now I plug in my stuff from my area function. Okay, let's pull out the pi and square everything. Let's simplify. Okay, the ones are going to cancel, and I'll be left with, let's see, y. Okay. Minus y squared over 4. Minus 2 y over 2 to the 4 plus y over 2 to the 8th. Okay. Let's go ahead and integrate that. Let's see, y squared over 2 minus y cubed over 12 minus, let's see, plugging in 2, I'll get, let's say 4 over 2, 2 minus 8 over 12 minus 1 over 8 times 32 over 5 plus 1 over 2 to the 8th. That's gross. But it's going to simplify a lot. Okay, so I get this. Now I just need to combine all these fractions. Let's see, what's the lowest common denominator? Oh, I don't know about lowest, but we could do 45 for sure. Let's see, so 90 over 45 minus 30 over 45 minus 36 over 45 plus 10 over 45. Okay, 60 minus 36, 24, 34 over 45. And that checks out. That is the answer. So yeah, this is maybe in the integrating is kind of gross. Setting it up is not too bad. It's just the same thing we've done so far. Okay, just in a slightly different guise. All right, that'll wrap up for this problem session. Let me know if you have any questions.